So our final presentation is histogram uniformization for digital image encryption, and Juliano Lima from Federal University from Pernambuco will be the presenter.
Hello, good morning, everybody. I'm Juliano Lima, and I will present the paper Histogram Uniformization for Digital Image Encryption. This work was developed by me and Ricardo Campelo de Souza. Here's the outline of this presentation. After a brief introduction, I will give some mathematical background related to finite field cosine transforms. And after, I will introduce the main idea of this work, the histogram uniformization based on the FFCT. I will describe some simulations we have performed and show some results and make some discussion. And finally, I will present the main conclusions of this work. Okay, nowadays, it's easy to send and receive image, video, audio using the internet and also mobile networks. Actually, there are different services where multimedia information can be shared. And in some of these scenarios, techniques for providing security are very important. Techniques for multimedia security can be classified in three main groups. The first one is watermarking. In watermarking, particularly in digital image watermarking, the main purpose is to sign an image in order to protect the image against malicious manipulations, for example, and also in order to provide the detection of authenticity of the image. In steganographic technique, the main purpose is to hide an important message behind the image. And in the encryption technique, an image, that is the plain text, is directly transformed in another image, which in this case is the ciphertext here. In this work, we focus on a specific feature required by an encryption technique scheme, the resistance against statistical attacks. So here, the main purpose is not to give a complete image encryption scheme, but the purpose is to give a technique in order to protect the image against statistical attacks. That is, the scheme proposed here should be part of a complete image encryption scheme. So here we introduce a technique to uniformize histograms of digital images with such a purpose, to protect the image against statistical attacks. The uniformization technique proposed here is based on the finite field cosine transform. Okay, we know the DCT, the discrete cosine transform. The finite field cosine transform, the FFCT, is analogous to the DCT, but here the transform is defined over a finite field. That is, here the FFCT can be applied to an image where pixels are integer numbers, and also the result is a matrix of integer numbers. Since the transform is computed over a finite field, it involves only modular arithmetic. And there are some important consequences of this fact here. The first one is that rounding is not necessary. This is very, very interesting. Another consequence of this transform is that efficient computations can be carried out. We don't need, for example, to perform floating point arithmetic operations. And consequently, coding and transmission are easier because we have just integer numbers also in the transform version of the image. I have to present some theoretical background related to finite field cosine transform. Actually, finite field trigonometric transforms were introduced 4 years ago, my PhD thesis, and we have a family of trigonometric transforms composed by 8 types of finite field cosine transforms and 8 types of finite field sine transforms. They are analogous to the DCT and the DST, but they have different properties. For example, we use DCT to compress images, for example. Here, this property is not present, okay, because the transform is defined over finite field. But we have other applications. At first, we have to define a cosine function over a finite field, and the cosine function is given by this expression here. The expression is similar to the expression using complex exponentials for the cosine function, but here, instead of using the Euler number, we use this number here, which is in a finite field GFP. The finite field cosine holds properties similar to those of the standard real-valued cosine functions, such as unit circle, for example, addition of arcs, but all computations are carried out over a finite field and not over complex number. Here we have the definition of the finite field cosine transform used in this paper here. The finite field cosine transform of a vector x, bold x, with elements in the finite field GFP is the vector capital bold X, where the elements are given by this expression here. We see that this expression is very similar to the expression for the DCT, but the difference is here we use the finite field cosine function instead of the ordinary cosine function. But the expression is very similar. The difference basically is that all computations are carried out over the finite field. And we can see that here we don't have the P over N. Okay? But here we also have this weight function, which is defined by this expression here, which is also computed over the finite field GFP used to define the transform. Okay, the computation of the FFCT, this is a linear transform, can be expressed by a multiplication between the transform matrix, which is denoted here by capital C, and the vector to be transformed. So this matrix is also can be inverted. The inverse transform of the FFCT is given by the matrix C transpose. And if we want to compute the FFCT of a matrix M or an image block, for example, we just have to compute the transform of the lines, of the rows, and of the columns of this matrix here M. Then we can just to perform this product here and compute the transform of this matrix here or this image block, for example. This matrix C, the transform matrix of the FFCT, has different and important properties. A property particularly important here is the period of the matrix C. The period of C is defined as the least positive integer number L, such that C to the L equals the identity matrix. Okay, we have to, the period is, if we take the matrix capital C and compute powers of C recursively, the period is the least positive integer number L, such that the identity matrix is obtained. And we remarked that it's possible to obtain FFCT matrices with large periods compared to the periods of other transforms. I will clarify the importance of this property in the next slides. So here is the basic idea of our method. The method is very simple. In order to uniformize the histogram of an image based on the FFCT, we just have to divide the original image into blocks of fixed size and take such blocks in a systematic sequence. And then we have to compute the FFCT a certain number of times of each block. Okay, there is a recursive application of the FFCT to each block of the original image in order to produce the image with the uniformized histogram. And in the paper, we explain that the tendency is that the application of the FFCT produces blocks composed by uniformly distributed symbols. Actually, there is not a mathematical proof for this fact here, but we have, in a paper published some years ago, we have analyzed this operation here and performed several statistical tests in order to assure that this result can be achieved by applying the FFCT to image blocks. So this procedure is invertible and does not involve any rounding error. Okay, in order to effectively implement the method, we have to define the transform. I had shown some slides ago, and we defined the transform to be used in this method by choosing a Fermat prime number, P, equals to 257, and use the number zeta equals to 128 to define an FFCT with length equals to 8, the matrix of which is given by this matrix here. So in order to compute the FFCT of each image block, we just have to compute the product between this matrix here and each 8 by 8 image block to be transformed. In this case, the period of this matrix is almost 17 million. So we have to compute the 17 millionth power of this matrix in order to obtain the identity matrix, or in order to obtain the original image again. So this is important because our method is based on the recursive computation of the transform of each image block. So it's important to have a large period because we can avoid that the image return to the original image after some recursive computations of the transform. So here is the first result of this method. We uniformized the histogram of the image Lina with these dimensions here. And in this case, the FFCT was applied only once to each image block. Then here we have the original image and its histogram. And here we have the transformed image using our method and the resulting histogram. We can see here that the histogram has a uniform aspect. So we have to apply the FFCT recursively because here we have one problem. If we choose P equals to 257 after computing the FFCT, the resulting image block can have pixels from 0 to 256. But we want to avoid pixels with this value, because if we have pixels with this value here, we have to use 9 bits to coding this value here. So we have to avoid these pixels with this value here, and in order to avoid pixels with values equal to 256, we apply the FFCT recursively. So we compute the FFCT of each image block until have an image block without pixels equal to this value here. If we avoid this, we keep the pixels range from 0 to 255, and this means that we can use an 8-bit coding to code the image. Then here is a block diagram of this procedure. We have the input image block here, and the FFCT is computed, and if necessary, the FFCT is recursively computed in order to produce an output image block without pixels equal to 256. So naturally here, the recursive computation of FCT will involve an additional computational complexity, because more transforms must be computed. So we can measure the effects of this additional computational complexity by counting the number of image blocks which need a determined number of recursive FFCT applications. We will show this measure here in our simulations. Okay, in our paper, we use some metrics to evaluate the proposed technique. The expressions of these metrics here are given in the paper. The first metric is the gray difference degree, the GVD, which depends on the average neighborhood gray difference of the image before and after the uniformization procedure. The closer to 1 the value of the GVD, the better the effect of the uniformization procedure. We also use the correlation coefficient, and we also compute the entropy of the uniformized images. Okay, our simulations run in MATLAB. We consider grayscale images with these dimensions here. And we have 6 test images. The original images are shown here. We have the transformed images in this line here. The original histograms, we can see that different types of histograms were considered, and in all cases, after the application of the FFCT, we got these uniform histograms here. And also, we have counted the number of blocks of test images submitted to recursive applications of the FFCT. And if we look to this row here, we see that almost 80% of the blocks had to be transformed only once. And a rather small percentage of blocks had to be transformed more than twice, which means that the recursive application of the FFCT does not represent considerable additional computational complexity. And the GVD is given here. We see that the GVD for all test images are close to 1. Okay. And also here we can see that the correlation coefficient for the transformed images, this how here, here, and here, is close to 0, as expected for the proposed procedure. Okay, the results are better than those achieved by traditional pixel scrambling approaches, such as those approaches based on the Arnold transform. And also for all images after the uniformization procedure, the entropy has assumed values in this range here, which is also satisfactory. So we can extend the method introducing a key. Using a key, we can select pixels, random or pseudo-random pixels, and compute the transform again in order to produce a complete encryption scheme. But this has a key. This work is currently under investigation. And finally, some concluding remarks of this paper here. Procedure to uniformize image histograms was introduced. And as the main advantage of this method here, we see that the proposed method involves modular arithmetic only, which suggests faster and computationally efficient implementations compared to other approaches. And as I said, the extensions of the method are currently under investigation, such as the application of the method to other media, such as audio and video. Okay, that concludes my presentation.
Questions? So, while you think I have more curiosity than a question, what is a statistical attack?
For example, if you just take the image, an original image, and just scramble the pixels, but if you don't modify the pixels, a third party can analyze the statistics of the image, just look to the histogram of the image. And in this case, maybe it's not so clear, but if you have, for example, a source where the number of zeros and ones are not balanced, then it's important that the source have random appearance. And if you do not modify the histogram or the relative frequency of zeros and ones, there are statistical attacks which allows the inference of some information related to the original image or the original data.
Thank you for a very nice presentation. And I have a curiosity also. So when you show your results, the number of times you need to compute once, all of them are like 78. Is there some explanation for that? Like 78% of the blocks don't need to be performed recursively. Because there are different images and they have different histograms, but it all got 78%.
Okay, let me explain. We first compute the transform, and we check if in the block we have pixels we follow 256. If not, okay, the block is processed. But if we have pixels with the value 200, the block has to be transformed again. So actually, there is no mathematical explanation for this fact here. But I believe we can we can make a statistical analysis of this fact, and in order to compute probabilities of this recursive computation is necessary or not. But we don't have this probability analysis yet.
Thanks, Juliano. So to finish this section, first of all, I would like to thank the presenters to control the time so sharply. Thanks a lot for that. You make my life much easier. And thank you everybody for coming.